All right, in this section, we're going to look at the method of undetermined coefficients, and we're going to use what's called the superposition approach. The fact that we're naming it the superposition approach suggests that there's another approach, which we will talk about in a coming section. All right, so first of all, recall, whenever you have an nth order homogeneous or actually in this case, non-homogeneous, right? Whenever you have a nth order linear non-homogeneous ODE, the way we're going to solve that, as we saw in a previous section, is we're going to find the complementary solution. Remember what the complementary solution is? You basically pretend this is homogeneous, pretend this is 0, and solve. In the last section, we saw a very nice method of doing that whenever you have constant coefficients. But one way or another, you find the complementary solution. And then what you do is you find the particular solution. That is to say, a single unique solution to this problem with this being g of x, not just 0. Okay? And once you find the complementary solution, which again, that's a solution to the associated homogeneous problem, and you find a single particular solution to the non-homogeneous problem, adding those together gives you your general solution. Okay? So now with characteristic equations, we have a way of finding this y sub c, at least under some conditions. Now we need a good way of finding a particular solution. Okay? Now the method of undetermined coefficients, it begins with, well, let's not sugarcoat it. It begins with a guess. This technique is essentially a method of educated guessing and checking. But it's a little more than just that, right? But ultimately it does boil down to we're going to take an educated guess and do our best to see if that works or not. Okay? That guess is going to, for a particular solution, should look like something given the properties of this input function, of this g of x. Okay? So essentially what we're going to do is we're going to consider, okay, what is this? Keeping in mind that when it's 0, we have our y sub c, so our y sub p comes entirely from this. And we're going to say, well, given whatever this is, there should be some characteristics that our particular solution will have. And we'll basically reverse engineer that. Right? Structurally, this might look a lot like partial fraction decomposition, at least superficially. Okay? All right, so a quick note on this technique for this section. Unfortunately, it is not all-encompassing. It doesn't work for all cases. However, it does work for a lot of common problems. Right? So there, if I think hard, or I could probably come up with a problem that this wouldn't work for. But for most common problems, for most common input functions, g of x, it'll work just fine. So this method does not work for all problems, but does work when g of x, that input function there, is the finite sum or product. And finite is important here. You can't have an infinite number of these, right? You can't say, oh, I can turn it into a power series. And no, it's got to be a finite. Is the finite, that's not to say there is no use for power series in differential equations, just not here. We'll see power series used later for a different purpose. So this does not work for all problems, but it does work when g of x is the finite sum or product of, well, let's see, I guess you can have polynomials, exponentials, sines, and cosines. And cosine. Notice that does include a very large number of common functions. However, it does leave out things like logarithms, right? So it doesn't work for absolutely everything. Let's see here. Okay, so we're going to begin with a small table. This is a table of what we're going to call educated guesses, because that's basically what it is. In fact, I'll even label it as such. Table of educated guesses for our particular solution. Okay, so if your input function, if your g of x is a constant, which constants are technically polynomials, then our particular solution should also be expected to be a constant. Does it have to be? Oh, well, we'll see. The educated guesses are a starting point. Oftentimes that will be the answer, but sometimes it'll require a little tweaking, as we'll see. But our starting guess is if your input function is a constant, your particular function is also a constant. So something like a. If your input function is linear, then your y sub p you would expect it to be linear, or at least something related to something linear. Quadratic, you would expect the answer to look something like ax squared plus bx plus c. And I think you're starting to see the idea here. Whatever this is, you're kind of expecting y sub p to have the same form. So for example, if you have a cubic, I'll guess what the expected result for y sub p is. Yeah, it's a cubic. Ax squared plus ax cubed plus bx squared plus cx plus d. Now, of course, we can do fourth and fifth and sixth, but I think you get the idea by now. But there are things besides polynomials on our list. What about exponentials? Okay, well, if you have something that is exponentials, then your guess is going to be some constant times some exponential. Where here the exponential might not be e to the x, it might be e to the 2x or e to the 5x or something like that. Okay? For sine and cosine, and that doesn't have to be sine of x and cosine of x. It can be sine of 2x or 3x or 4x. In fact, same thing over here. I should write that. It can be e to the x or e to the 2x or e to the whatever x. Same thing with sine and cosine. They don't have to be just sine x or cosine x. They can be sine of 2x, 3x, 4x, or whatever we need. Okay? In either of those cases, the expected y sub p is going to look exactly the same for both of these. They're both going to look like a sine of ax plus b cosine of ax. If you have one, you expect your y sub p to look like a combination of both of them. And that's true for both of these. And if you have any product of these, so for example, let's say I had quadratic times a sine function, so x squared sine of 5x. If I have the product of any two of these, then it's going to be the product of these results. So for example, my input function is x squared times sine of x. Then I expect my final answer to be ax squared plus bx plus c times a sine ax plus b cosine ax. Something like that. I would expect the product of input functions to yield the product of particular solutions. But with something like this, there's not much more to it than to actually start doing these problems and seeing how they work out. Okay? So let's have a technique. To organize our method. All right, so to solve something that looks like a sub n nth derivative of y plus a sub n minus 1 n minus first derivative of y plus dot 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 plus a sub 1 y prime plus a sub 0 y equals g of x. What we're going to do is, and here we're assuming we have constant coefficients, so let's write that, where a sub 0, a sub 1, all the way through a sub n are constant coefficients. At least for now. We're going to take 3 steps here. First, we're going to find the complementary function y sub c, the complementary solution. Y sub c, which is the solution to the exact same problem, but homogeneous. All right, so here you take the exact same problem, but pretend g of x is equal to 0. So solving this is going to give you y sub c. And we know how to do this since these are constant coefficients. We're going to use the same technique from the last section. That is to say, we're going to write the characteristic polynomial, we're going to factor, and we're going to use that to solve. Okay, so we already know how to do that. Second of all, we're going to go ahead and find the particular solution. It is very important that we find the complementary solution first and then the particular solution. And you say, well, why is that? I need to find both, so does it really matter which one I find first? So the table of educated guesses isn't called the table of definitive guesses, or even more, right? It's not called the table of definitive answers. We know for a fact these will work. No, these are guesses. And sometimes these guesses will be wrong. Well, how will I know? The complementary solution will tell us that. Y sub c will tell us whether our guess is right or not. So we need to know it first. Otherwise, we'll find our particular solution through our educated guess, and then, it's wrong. So we need to find y sub c first, because it will inform us whether or not our guess for a particular solution is correct. And if it's not correct, we need to know that so we can modify that guess. Okay? So it does require us to do it in this order. So first the complementary solution, then this one. Find the particular solution, y sub p, using the table of educated guesses. Then solving for the A, the B, the C, the however many you might have. Okay, and then finally, the last one is the easy part. Y will equal to the y sub c that you found in the first step, plus the y sub p that you find in the second step. And that is our technique. So let's begin with one that's nice and simple, and everything works out perfectly. Everything works out exactly the way it should. And then we'll look at somewhere, maybe there's a little something that goes wrong. And then we'll see how to fix that, yeah? All right, so let's start with y double prime plus 4y equals x squared. All right, so start off with the associated homogeneous version of this problem. Okay, so first we're going to solve y double prime plus 4y equals 0, the associated homogeneous case. Okay, well that's something we know how to do already. We can find the characteristic equation to be m squared plus 4 equals 0. We could use the quadratic formula, I suppose, but it's much easier to just say, well, subtract 4 to the other side and then take the square root. So m is equal to plus or minus the square root of negative 4. Or in other words, it's plus or minus 2i. Okay? Keep in mind that plus or minus 2i is the same as saying 0 plus or minus 2i. So this is the real part. This is your a. And the imaginary part, that's your b. So now thinking back to our previous section, we can now write our solution to this, our y sub c, as, let's see, it's going to be c1 e to the real part. So that's going to be 0x times cosine of the imaginary part times x, plus, and then the exact same thing, but with sine instead of cosine. So e to the 0x sine of 2x. Although this is correct, here e to the 0 is just 1, so you're probably better off writing it just as c1 cosine of 2x. Since you're here, you're just multiplying times 1. So c1 cosine 2x plus c2 sine 2x. All right, so there we go. That is the first part of our answer. That's the complementary function. Okay. Next, what we want to do is we want to find our particular solution. Okay, so we're going to go ahead and take a look at our table of guesses and say, well, this is x squared. That is a quadratic. So our educated guess is that our answer should look something like this. Okay, so educated guess. is that our y sub p will look something like ax squared plus bx plus c. Okay, so now we simply need to take this, plug it into this equation, right? We already know y is going to go in there. We're going to take the second derivative, plug it in there, and see if we can't solve for that a, b, and c there. All right, so let's give this a try. If y sub p is going to look something like this, then y sub p prime, well, that'll be 2ax plus b. Now derivative of c, derivative of constant 0. And then the second derivative, that's going to be just 2a. The derivative of b, the derivative of constant is 0. Okay? So now we can take those and plug those back into our starting equation. So y double prime plus 4y equals x squared. That's going to become, okay, well, y double prime, I just replace that with 2a. And then plus, and I've got 4 times y, so each of these is going to be multiplied by 4. Right? This is my y, and I want 4 times that y, so all of those get multiplied by 4. 4ax squared plus 4bx plus 4c, that's a square, equals to x squared. And I mentioned earlier that, at least superficially, this really does look a lot like solving for partial fraction decomposition. And that's what I meant. When you get to this point, it really does look like partial fraction decomposition. You're simply setting up a system of equations based off the a, b, and c, and solving for those a, b, and c. All right? So our system of equations is, all right, well, let's see. I have x squared on this side, and that's got to match the x squared on this side. That's what equal means, right? The left side and the right side must be the same. So 4ax squared must equal to 1x squared, because the square has to match the square. Oh, so then 4a must equal to 1. Here I have a single linear expression, 4bx. Over here I don't have any, or I guess you could say I have 0x. Okay, well then that means that the 4bx has to equal to 0x. So 4b must equal to 0. And finally, my constants, the ones that don't have any x's, that's 2a and 4c. Now over here I don't have any constants, so I guess you can just say that's constant is 0. So that means that the 4a combined with the, the 2a combined with the 4c must equal to 0. Okay, so 2a plus 4c equals 0. There we go, we have a nice little system. This top one is nice and simple, just divide by 4. This middle one is nice and simple, just divide by 4 as well. Here b is equal to 0. And this one, we just substitute. So here I've got 2 times a quarter, because we know a is a quarter, plus 4c equals 0. So here that's what, 1/2, which I can subtract to the other side. So that'll give me 4c equals -1/2. Divide both sides by 4, I get c equals -1/8. And there we go. I now know the a, the b, and the c for this y sub p. So y sub p is equal to, my a was 1/4, so I get 1/4 x squared. B was 0, so I can write 0x, but I'm probably better off just leaving it off. And then my c was -1/8, like so. And there's my y sub p. Thus, I have my final results. My general solution is going to be y sub c, which is this stuff, plus my y sub p, which is this stuff, and so I'm done. I get c1 cosine 2x plus c2 sine 2x plus 1/4 x squared minus 1/8. This is our result. This is an example where absolutely nothing goes wrong. It works as perfectly as you could hope for. This factors out, we get a nice simple characteristic equation. It factors out or solves nicely. We get a nice predictable solution. Then our educated guess, we solve for the a, the b, and the c. Everything works out nicely. And then we just stitch the two together. This works really well and fairly simply. But, as I mentioned earlier, there is a reason why we find y sub c first. And that is the possibility that our educated guess is wrong. You say, well, how could it be wrong? Because our complementary solution up here is going to be made up of terms, cosine, sine, or exponential plus exponential, or some combination thereof. This y sub p has to be unique. It's got to be distinct from this. So let's say, for example, my educated guess gave me something that looked like 1/4 x squared minus 1/8 sine of 2x. That's clearly wrong. You say, why? Because that 1/8 sine of 2x would be part of this. Okay, so then part of the thing that I thought should be there isn't actually there. So I have to modify what I thought should be there in some way. Right? This can be circumvented, but it takes careful modification of our guess. And let's go ahead and take a look at one to show how that actually works. Okay, so let me go ahead and try this one here. We're going to go ahead and solve the equation y triple prime minus 2y double prime minus 4y prime plus 8y equals 6x e to the 2x. All right, let's give this a try. So first, let's find our complementary function. All right, we're going to look for our y sub c. All right, well, that's simple enough. We're going to go ahead and consider the homogeneous version of this problem. Y triple prime minus 2y double prime minus 4y prime plus 8y equals 0. That would then give me a characteristic equation of m cubed minus 2m squared minus 4m plus 8 equals 0. Here, you can actually find this one by factoring, by grouping. You may or may not remember this, but grouping is whenever you have an even number of terms greater than 2. So if you have 4, if you have 6, if you have 8, what you can do is you can just look at the first half separately the second half. In the first half, I notice I have a common factor of m squared. In the second half, I notice I have a common factor of negative 4. Notice that is still negative 4m plus 8. But now, these two halves have a common factor of m minus 2. So here I have m minus 2 is my common factor between these two halves. And then m squared minus 4 is my remaining factor. Oh, but m squared minus 4 can itself be factored as the difference of squares. M squared minus 4 can be factored as m minus 2 and m plus 2. So I get three different results here. I've got m1 equals 2. I've got m2 is also equal to 2. And I've got m3 is equal to negative 2. So that means that my y sub c is going to equal to, all right, so looking at the first two, those repeat. Oh, and I know how to do that. I know how to deal with two real solutions from a characteristic equation that repeat. What I do is I write the first one as c1 e to that number times x plus, since the next one is going to repeat, it's going to look exactly like this one, but times an extra x. It's going to be c2x e to the 2x. This one right here is, okay, so now we've done those two. So now let's move on to the next two. Okay, well now that's distinct. This is different from any of the ones we've had before. Okay, so then we start the count over again. We don't have an extra x on this one. And now we're back to c, in this case c3, since it's the third one, times e to the minus 2x. And there we go. This would be our complementary solution. Okay, so now we want to find our particular solution. Okay, so we would take our educated guess. We know g of x is going to be 6x times e to the 2x. And that's the product of something linear and something exponential. Okay, so, oh, that's the wrong page. So, in our table of educated guesses, if you have something that's the product of two things, you just take the two guesses for those two input functions and multiply them. Okay, so I have something linear times something exponential. Okay, so for linear, I use ax plus b. And for exponential, I use a times e to the power x. Okay, so my educated guess is going to look like, for my linear part, I'm going to have ax plus b. And for my exponential part, I'm going to have some constant, which I'll call c, times e to the 2x, like that. Oh, but we have a little problem. What's that? That's already our answer. Notice, a constant times e to the 2x. All right? In fact, let me write that. Right? If I were to multiply this, ax times this, I would get what? I would get a times c is just another constant. So, some constant, I'll call it c, whatever, c5, c4, whatever, times x e to the 2x. And if I were to multiply these, this b times this c would be some other constant, c6 e to the 2x. Notice we already have those. A constant times e to the 2x, a constant times x e to the 2x. That's a problem. Because since these terms are already duplicates of this, we don't really have a particular solution. The particular solution is supposed to be distinct from the complementary solution. The complementary solution is for the homogeneous case. The input function is supposed to give us something extra. That's not extra. We already have that. So we're going to need to modify our guess so that it doesn't overlap with our current solutions from our first part. Thankfully, mercifully, that's easy to do. So here, let me put this as a note. If any terms in our guess are duplicates of terms in y sub c, you're going to multiply your guess by x to the power of n, where n is the smallest whole number that gets rid of any duplication. So technically here not technically, there's nothing technical about it. It is. We've duplicated both of these, okay? So, I should finish writing this. Where the smallest whole number that gets rid of all duplications. There we go. So here, we've duplicated both of these. Okay, so here's what we're going to do. We're going to take our initial guess, and we're going to multiply it by x to a power. Now, you don't want to go too big. You don't want to go x to the power 50 right off the bat. What you want to do is you want to use the smallest one possible. Okay, so right here, if I've got ax plus b times c e to the 2x, if I multiply that by x, okay, now each of these is going to have an extra x on it. So this will be x squared e to the 2x, which we don't have any of those. Okay, cool, so that's not a duplicate anymore. But then this one will become x e to the 2x, which we do have one of. So a single x is not enough. It makes this one not a duplicate anymore, but this one still is. So go up another step, x squared. If we multiply all of these by x squared, this becomes x cubed e to the 2x, which we don't have one of those. And this becomes x squared e to the 2x, which we don't have one of those. Okay, so this is the smallest whole number that we can multiply this by so that we don't have any of these duplicate any of those. So this is our new guess. Okay, so let's go ahead and write this as, let's see, I'll have ax cubed. Let me distribute this into those. Ax cubed plus bx squared. Right here, these already have constant coefficients. This c right here is just another constant coefficient. But when I multiply a times c, and when I multiply a constant times a constant, I just get another constant. And likewise here, when I have a constant times a constant, I just get another constant. So here, this and this constant already cover this. So you know what? Let me not even worry about c. I'm going to just leave it off. You say, can I leave c there? You can. in which case you could distribute and end up with something like this. But I'm just going to keep it simple and say, well, you know what? These already have me covered. These are already coefficients. I don't need this extra one. Okay, so let's see. So now we're just going to go through the same process that we did for the last one. It's a little more complicated now because the problem's a little bit bigger, and it required this modification of this multiplication by x to the n. But aside from that, once we've done that, this is the same kind of problem. So now what I'm going to do is I'm going to find up to the third derivative. Now here I need to go up to y triple prime and then plug all those in. So let's give this a try here. If I've got y prime, oh, let's see, I guess for y prime, I've got a product rule. So it's going to be the derivative of the first one, 3ax squared plus 2bx times the second, plus, now you leave the first one alone, ax cubed plus bx squared, and then the derivative of the second, that's going to be the derivative of e to the 2x is, again, e to the 2x, but then times 2, because of the chain rule. So that's going to give me, e to the 2x is a common factor, which I will factor out. So I'm just going to combine all of this stuff. So here I've got 2ax cubed, 3ax squared plus 2bx squared. Okay, so that's going to be 3a plus 2b x squared. And then I've got 2bx plus 2bx times e to the 2x. Okay. So now I need the second derivative. Starting to wish I'd picked the smaller one. This is going to get pretty big, but oh well, it is what it is. And again, I have to use the product rule. First, derivative of the first one, that's going to be 6a x squared plus, now the derivative of the second one, I'm going to bring my 2 down, so that'll make that 6a plus 4b times x plus just 2b times e to the 2x plus, so now I leave this first one alone, 2ax cubed plus 3a plus 2bx squared plus 2bx times e to the 2x. Again, the e to the 2x is a common factor, so I will factor that out, and I'll just worry about combining this polynomial part. So here I've got a cube 2ax cubed. 2ax cubed. I've got a square here and a square here. So I can combine the coefficients of the squares. That will be 6a plus 3a. That'll give me plus 9a plus 2bx squared. Plus, let's see, I've got linear right here, x and x. So that'll be 6a plus 4b plus 2b. That'll be 6a plus 6b. 6a plus 6b times x. Plus, and then I've got just a single constant, which is 2b, and all that times e to the 2x. Oh, wait, no. I've made a mistake here, haven't I? Because here, I left the first one alone, and then take the derivative of the second one. I have to use the chain rule and multiply this whole thing by 2. So that's not right, is it? So here, this should be double all of these. So that's going to be 4ax cubed, not 2. So that's going to be a 4 there. Okay, and then for my square, I've got 6a, and then doubling this one, that's another 6a, so that'll be 12a. So that's going to be 12a x squared, and then here I'm doubling this 2, so that'll be plus 4b. Okay, and then for my x, I've got 6a plus 4b, and then double 2b, that's another 4b, so that should be 6a plus 8b for my x. And then my constant doesn't change because my constant wasn't in the part that's being doubled, so 2b stays 2b. Okay, let me check that again. Now I'm paranoid. Yeah, I think, yeah, that's right. Okay, so that's y double prime, and I need y triple prime. So I got to do this one more time. Okay, so same idea. We're going to take the derivative of the first part. So that's going to be 12ax squared plus, here we'll bring down our 2, so that doubles these numbers. So that'll be 24a plus 8b x plus, that's going to be 6a plus 8b. And then here, this is a constant. The derivative of a constant is 0. That's e to the 2x plus, now I leave the first one alone. It's going to be 4ax cubed plus 12a plus 4bx squared plus 6a plus 8bx plus 2b, with all that alone, exactly as it was. And now taking the derivative of the second one, the derivative of e to the 2x is itself, but then everything's going to be by the chain rule multiplied by 2. So again, just like in all the previous ones, e to the 2x is a common factor. So I'll just multiply the polynomials and leave the common factor till the end. So let's see, I've got 8ax cubed. And then for my quadratic, I've got 12a plus 12a. That'll give me 24a. Plus 4b is being doubled, so that'll be plus 8b. Let's see. Right, yeah, so there's no other b over here, so that's just going to be plus 8b x squared. And then for linear, I've got this one plus double this, so 24 plus 12, that's 36a. And then 8b plus double 8b, that's going to be 24b x. And then for my constants, I've got 8b plus 2b right here. That's going to give me 10b. And then the 6a is just going to stay as 6a. So 6a plus 10b looks like that. Oh, nope. I made a mistake again here. So that's 8b plus double 2b. So 8b plus 4b, that'll be 12b right there. So 6a plus 12b. Oh, and right here for my square, I've got 12a x squared plus 24a. I didn't see that there was another one up here. So double 12 is 24, but then another 12. That'll be 36. These get big, don't they? Let's see. Yeah, okay. So that's good now. All right, so let's see. So I've got up to triple prime, and so now I can just go ahead and plug all this in. Oh, that's going to be a whole lot of arithmetic. So I'm going to take my y triple prime. So that's all this stuff right here. So that'll be 8. I forgot to write my e to the 2x there. So that'll be 8a x to the power 3 plus 36a plus 8b x to the power 2 plus 36a plus 24b times x plus 6a plus 12b, like that. And notice that every single one of these is going to have a polynomial times e to the 2x, polynomial e to the 2x, polynomial e to the 2x, polynomial e to the 2x, which means that when I plug them in, every single one of these is going to have e to the 2x as a common factor. So I'm just going to go ahead and write e to the 2x at the very beginning and then not worry about writing it ever again because it's going to just distribute to all the rest of them. Okay, so I've got my y triple prime, which I've written down here. And then I've got minus 2y double prime. Okay, so here's my y double prime. Again, my e to the 2x, I've already written that there. So just all of this times negative 2. Okay, so let's see. Negative 2 is going to give me negative 8ax cubed. Double these and with negatives. So that's going to be negative 24a minus 8b x squared. And then again, doubling these and making it a negative. That'll give me negative 12a minus 16b x. And then finally, multiplying this by negative 2 would give me minus 4b. Okay, so then my next term is going to be negative 4 times y prime. Okay, so here's my y prime. And I'm going to multiply that times negative 4. So let's see, negative 4 times 2ax cubed, that's negative 8ax cubed. And then multiplying these by negative 4, that's going to be negative 12a minus 8b x squared. And then here times negative 4, that's going to give me plus a negative 8bx. And then here there's no constant for that one. And then finally the last term is 8 times y. It's going to be 8 times y. Here's my y. And so it's just going to be 8 times this. Again, my e to the 2x, I've already got it there. So 8 times this is going to give me 8ax cubed plus 8bx squared. And that is positive, yeah, plus. All of that. And that's supposed to equal to, if I add y triple prime minus 2y double prime minus 4y prime plus 8y, I'm supposed to get 6x plus e to the 2, times e to the 2x. Okay, well obviously this matches this, so we can just divide both sides by e to the 2x, and so just all of this has to equal to 6x. The way I've written it here makes it easy to note that all of these cancel out. 8 minus 8, 8 minus 8, ax cubed, this is all 0. Okay, cool. Let's see, what else? Over here, 24 and 12 is 36, so negative 36 plus 36, that'll cancel. That's all gone. And then here I've got 8b minus 8b, 8b minus 8b. These all cancel. So that's all gone. Isn't that nice? Oh, let's see. And then for my linear expressions, unfortunately these do not all... Oh, I was going to say unfortunately they don't all cancel out. Actually, it's very fortunate. Otherwise we would not be able to solve this. So it's very fortunate these don't all cancel out. I've got 36a minus 12a. That's going to give me 24a. And then, let's see, negative 8 and negative 16 is negative 24b. And that'll cancel this positive 24b. So this is 24ax. Plus, and then over here, nothing cancels, so I just combine those. I'm going to get 6a. And then 12 minus 4, that'll give me 8b is equal to 6x. And in spite of all of that very tedious derivation and combination, in the end we get a very nice simple result. Here, our linear coefficient must match this linear coefficient. I must have 24a is equal to 6. And my constant here must match my constant over here, which of course is 0 since there is no constant. So that's going to give me 6a plus 8b equals 0. That's a nice little system. I can divide both sides by 24, so this will give me just a equals 1/4. And then here I can plug in my 1/4 that I now know. So 6 times 1/4 plus 8b equals 0. Let's see, what's that? 3/2, which I can subtract to the other side. 8b equals negative 3/2. And then divide both sides by 8, which will give me b equals negative 3/16. And so those must be my coefficients. Going back to this previous page, we see that those coefficients are the coefficients here and here. So now we have our result. So y sub p is going to equal to, let's see, we were supposed to get a, which is 1/4, times x to the third, plus b, which is negative 3/16. Since this thing plus a negative, I'll just write minus 3/16 x squared. And that will be multiplied by e to the 2x. I've got my ax, my new guess was a x cubed plus bx squared times e to the 2x, where the a and the b were what we found here. Our a was 1/4, and our b was negative 3/16. So in spite of a much bigger problem this time, we ultimately get the same kind of answer. So now we have our complementary solution from up here. This is our y sub c. And now we have our particular solution here, our y sub p. So finally we can answer our question. The solution to our third order differential non-homogeneous equation is y equals, we're going to take our complementary solution c1e to the 2x plus c2x e to the 2x plus c3e to the minus 2x, and then we're going to add in our particular solution. If you want to write it exactly the way it is here, awesome. If you want to distribute, that's fine too. I will distribute just to make it look, just so I can highlight something here in a moment. I'm going to go and distribute this. So my particular solution will be 1/4 x cubed e to the 2x minus 3/16 x squared e to the 2x. And that would be our solution. Notice here that by having modified our problem at the beginning of this second step by saying, oh, these repeat these, and we can't have that, so we multiplied by x squared. What that does is it makes our particular solution have the smallest power of its x being squared, which puts it above any of these. All of these are either just exponential or exponential times linear. These are exponential times quadratic or higher. So this right here is our general solution, and that is our final result. So that is it for this topic. That is it for this section. If you have any questions, comments, or problems, please let me know. Otherwise, I hope you all have a nice day.